Wow, okay. So now, let's talk about typical requirements and design considerations. Typical requirements for the thermal subsystem. As always, you want to think about size, weight, and power. You want to think about the component's operating temperature range and storage temperature range. And you also want to consider the structural stress due to thermal expansion. The reason why you care about this is because thermal cycles can lead to thermal fatigue and structural failure, where your coefficient of thermal expansion causes your component, like this fuel cell, to shrink and expand, but these different nodes are constrained due to bolts or whatever confining geometries. And because of that thermal expansion, there's some structural stress and therefore structural fatigue that you need to worry about. So there's a question here. The thermal control system supports the other subsystem designs and interfaces between thermal connections. So this subsystem is the one that has to be flexible and rigorous at the same time, because the engineers won't know what parts of the system need to have specific requirements until suggestions are made. And yes, that's true to a point. I think that all subsystems have their hard parts, but the thermal subsystem lead, I think, has to be one of the more resourceful and adaptive of the engineers. It's right that you have to select a component to know what acceptable operating range there is. And then the thermal control lead needs to be attentive to that. So you do have to wait for some of the design to occur before you can really start your job. But also, as a thermal engineer, you accumulate experience and intuition as to the general arrangement of a spacecraft, which can guide you in forming kind of a general picture of it. I mean, there are things you can control for beforehand, like generally you know what the orbit is and what the space environment is. You know whether the spacecraft is going to run. If it's interplanetary, it's most likely going to be cold. But yeah, there is a little bit of waiting to understand the power dissipation of the components inside and their individual temperature ranges. Okay, external requirements. So thermal doesn't have too many. From the CubeSat design specification, pretty much there's the thermal vacuum bakeout test, and then tests defined by the launch provider. Our launch provider is most likely NanoRacks, in which case the CubeSat shall be capable of withstanding the expected thermal environments for all mission phases given here. Okay, pretty straightforward. Now let's talk about the process. There are specific processes in which we need to instill requirements, like during the manufacturing and assembly process, we want to make sure that there's proper contact between components, and this is a quality assurance step. We also want to make sure during testing that our thermal vacuum chamber tests replicate the space environment and we observe system behavior to compare against model predictions. And we saw from the external requirements that during transport and rehandling, you need to survive storage conditions in various environments. So there's a question here, that's a good one. If components are only tested using FEA and not physically, are they still allowed to be used for spaceflight? So this is certainly true for the CSLI provider, but I'm not sure that it's true for all providers. If we're thinking more rigorous NASA flagship missions, I would err on the side of no. But for our purposes, we can, if there is a lot of certainty around the thermal analysis. Another question, are all these tests able to be done at HSFL in the basement? And so I have pictures of what's available in the HSFL in the post-building basement. Here is Amber, our avionics engineer, inside the Intelvac thermal vacuum chamber. It's in the HSFL cleanroom facility. It's a 1.6 meter by 2.25 meter cylindrical horizontal chamber. So you can see Amber crawling in there if it's human beings. We also have one that does not so much fit human beings. It's a smaller one. This smaller vacuum chamber is used primarily for assembly outgassing and thermal stress testing. Okay, design considerations. Yes, so we've talked about some of these already. What you can consider for your spacecraft design is the environment that it will see for the orbit that you chose for it. You can think about it in LEO. You can think about it in interplanetary and on planetary surfaces, for example. You should also think about the power dissipation from your electronics. You should think about geometric placement with respect to sensitive components in space environment. And you should think about how you distribute components that like to be hot or cold. So these last 2 points are demonstrated with this picture of the James Webb Space Telescope, where there are 2 sides of the James Webb Space Telescope. There's a hot side, which is facing the brunt of the sun, the solar radiation. And then there's a cold side, where this heat shield separates the hot and the cold side. So yeah, you can see this geometric placement in play here, where this hot side is facing the sun, the instrument and such as the detectors and filters are facing away. And you can see the distribution of components. So these, the solar panel, antenna, computer, and reaction wheels, those like to be warm. So you bunch them together. And then on the other side, the science instruments, the mirrors, they like to be cold. So that's where you would bunch them on the other side. Okay, and then there were questions. There were 2 people who caught that I said that you need to keep RTGs hot, and that is a mistake. You need to keep RTGs cool. So good on you for catching that error. And then there was a question about thermal cycling. Doesn't this happen every time orbiters enter direct sunlight, then pass behind a planet like Earth? Yes, this is true. Thermal cycling absolutely does happen every time a satellite transitions from sunlight to eclipse. Not all components are affected equally, though. Some components in the center of the spacecraft are more insulated from thermal cycling, whereas the outside is most affected. You can think of solar panels and antennas as being one of the more affected components. All right.